And the last theorem that I want to prove today, or the last thing, is that differentiability.
A huge thanks to Brian for sponsoring this video.
Good morning, fellow mathematicians, welcome back to another video, and today is gonna be quite fun. I thought I might present to you 5 of my most favorite short proofs today. They are nothing too complicated or groundbreaking, but they serve as a little aha moment because they are just cool in general. You probably have a short or cool proof too that you might want to present to the audience here, so leave some comments down there below if you can come up with something that you think is pretty cool and someone else should see it. So I hope you're going to enjoy the video, and this video has been sponsored by the wonderful people over on Brilliant. More information at the end of the video. Stay tuned, they provide a great service to the STEM community. And now we are going to dive right in. Those 5 short proofs are going to be part of different branches of mathematics, and we are going to start off with group theory because I have done a bit of group theory in the last few videos. And this was one of the first proofs I have ever seen at university, and this is mainly concerned with the identity element in a group. It can also be the identity function, for example, or any other identity. It really doesn't matter. It does hold. What is an identity? Just for clarification, take the number 1 under multiplication. 1 times any other real number is just a real number in and of itself. An identity element just preserves any other element in a group, ring, field, whatever. So we are going to show today that the identity element inside of an algebraic structure or of a function, etc., is actually unique. Meaning there's only one, just like the number 1 under multiplication. It's a unique element. How can you show something like this? Well, we are going to do a proof by contradiction. We are going to suppose that there does exist another identity element. We are going to call it identity start, element of an algebraic structure A, such that the identity element start in composition or whatsoever with the binary operation, whatever that's supposed to mean right here under the algebraic structure, with any element is equal to the element of an itself for A element of G. No, A, capital A. So this is what we want to show. Now, how can you go about something like this? Well, if we have an algebraic structure and it does have an identity element, we are just going to start off with the regular old identity element. Namely, we are going to say the identity element is equal to. Well, if identity start is also an identity, then it really wouldn't change our original identity if we apply it to this identity. So this is the same as identity in the binary operation with identity start. Now the cool thing about identity start is that's an identity, just like the regular identity. So if we use the regular identity on identity start, it's going to keep identity start how it is. So this right here is just identity start. You see something, it says that identity is equal to identity start. So those two are the same. 1 is equal to 1 indeed. So the identity element inside of an algebraic structure is unique QE motherfucking D. We are already done with that. And that is such an aha moment proof. I just love it. I really love this proof, and you should love it too. Okay, now you know about it. Show it to your friends next time you see them at the bus or at work. I don't care. Now the next one is from my linear algebra class, and this was one of my most favorite what the fuck proofs that I have ever seen. And it really depends on your ideological and also logical system if you really agree to what I'm saying here right now. Namely, that all round triangles are blue. You might say now, what? There don't exist any round triangles. And you are right. And this is exactly why I am right too. Let us write out the statement at first. So, all round triangles are blue. We are going to turn this into a logical statement. What does this say right here? Well, this just says that for all round triangles, I'm going to call them T, it does hold that the triangles are blue. This right here is just a regular old statement. Now what we are going to do is we are going to negate this statement right here. So we are going to take our original statement and we are just going to negate it, the entire thing. We are just going to take the vice versa thing basically. So instead of saying for all round triangles, we are going to say that there does exist a round triangle. Okay, that's just a negation of this. So this right here is equivalent to saying there does exist a round triangle T such that, and now we also need to negate the second part right here. Well, the negation of T are blue is that the triangles are not blue. And now here comes the springende Punkt, the jumping point, as you want to say in German. There does exist a round triangle. Well, obviously, this is your first instinct. There don't exist any round triangles out there. Well, this is exactly why this statement right here is now false. Now, what happens if a false statement is false? Well, this is just meaning that our original statement is true. That's a proof by contradiction. Just what we did up here, just a bit more formally. So, next time you go around to your family and say, hey, all round triangles are blue, you are indeed right if you exist. If you just accept the fact that there don't exist any round triangles. So it's really debatable if the original one is actually true. But by this logical chain that we did right here and the proof by contradiction, it just holds. It is indeed true. It's just what I love about logic. It's just so not logical at all sometimes. All round triangles are blue. That's great, right? Okay, this right here was the second proof I wanted to show you. Now, two proofs involve the square root of 2 in some kind of way. And this next one is one that I have presented here on this channel already, but it's always worth just repeating and showing once again, because it's just such a fabulous and ingenious proof. I just really like it. Namely, what we want to prove is that if we take an irrational number and all of this to an irrational power, we can get out a rational number. So irrational to the rational power can be rational. How can you prove something like this? Well, we are going to start off with the square root of 2. This, we all know, is an irrational number. Now, what we are going to do is we are going to raise it to an irrational number power. It doesn't matter which one, we just want to prove that irrational to irrational can be rational. So why not take the square root of 2 yet again? So we can either have two cases now. The first case being that square root of 2 to the square root of 2 is rational. If this is the case, then we are indeed done. Then there would be nothing else to do. Now the second case would be that this number right here is irrational. Square root of 2 to the square root of 2 is irrational. Well, if this is the case, we are not really done. But what we know now is that this right here is an irrational number, and we just want to prove that irrational to rational power is indeed rational. So why not raise this to an irrational power, let's say square root of 2 once again? So what we're going to do is we are going to take square root of 2 to the square root of 2, and we are going to raise it to the power of square root of 2. Now, by exponentiation laws, we can drag the square root of 2 down here. So that's the same as square root of 2 times square root of 2 times square root of 2. To the square root of 2 times square root of 2. That's a mouthful. Now, square root of 2 times square root of 2 is square root of 2 squared. This is the same as just 2. So this right here is square root of 2 squared. But square root of 2 squared is the same as 2, which is indeed a rational number. And so we have proven by this casework right now, and this is a direct proof, that rational to the rational power can indeed be rational. Ingenious, right? I really love this proof. I didn't come up with it. It's a classical proof, but it's just wonderful. It's just a wonderful proof and one of the most magical proofs I have ever seen. And now, next, we are going to kill a tiny little fly, a little flea. We are going to kill a hydrogen atom with a hydrogen bomb. We are going to throw everything out of the window, and we are going to prove that the nth root of 2 is irrational. So we know that the square root of 2 is an irrational number. Now we want to show that the nth root of 2 is indeed an irrational number. And we are going to do this by proof by contradiction. we are going to suppose that the nth root of 2 is indeed rational. And n just means all natural numbers greater than 2. Strictly greater than 2. I'm going to put this here for n strictly greater than 2. Now, if this right here is indeed rational, then that would mean that we can represent it as a divided by b, for example. Now, if we can represent it by a divided by b, we can just play around with this expression a tiny bit. We are going to raise both sides to the n power to get our root away. So this right here results in 2 is equal to a to the nth power divided by b to the nth power. Now, multiplying both sides by b to the nth power is going to result in 2 times b to the nth power is equal to a to the nth power. Now, 2 times something is just the something plus the something once again. So this right here results in a to the nth power is equal to b to the n plus b to the n. And this is where the proof by contradiction comes in. Does this seem familiar? This right here is Fermat's last theorem, and it states that there are no integer solutions to this equation for n strictly greater than 2. We know that Papa Pythagoras can hold, but for any n greater than 2, this is why I specified it here, it just doesn't work. This right here is contradicting Fermat's last theorem. And that's why I said we are going to kill a fly with a nuclear bomb. We are going to take something like Fermat's last theorem for granted, and then you just prove that something stupid like this is actually true. That the nth root of 2 is irrational. Take this to your party next time. Everyone is surely going to love it. But this is also a fun proof, and I have found this ages ago somewhere on Reddit, I think. It's just a fabulous proof that employs the fundamental theorem of our boy Fermat, which just can't fit into any kind of margin. Fermat's last theorem. And the last theorem that I want to prove today, or the last thing, is that differentiability implies continuity. So if a function is differentiable, then this implies that the function must also be continuous. It's an ingenious little proof, and I want to prove it in a second. Now, first things first, the converse statement is obviously not true. Just because a function is continuous doesn't mean that it's differentiable. It does make sense if you think about the absolute value. This thing right here is indeed continuous, but you can find a tangent to x being equal to 0, because you really can't decide if the tangent line would be tangent to this one or tangent to this one. So it's not differentiable in the regular sense. But if the function f is differentiable, then this does imply that it is indeed continuous. So we need to talk about two things here at first. What does it mean for a function to be differentiable at a certain point x0, or just an x value x0? That just means that the following limit does exist. The limit as x goes to x0 of f of x minus f of x0 divided by x minus x0. This is what it means for a function to be differentiable. Now, what does it mean for a function f to be continuous at the point x0? This just means that if we take the limit where x goes to x0 of f of x, this results in the limit being dragged into the argument. So f of the limit as x approaches x0 of x, which is just f of x0. Now, please note that this right here is indeed a constant. And the constant is not affected by a limit. So we can actually rewrite this a tiny bit. We are going to take the right-hand side here, and we are going to drag this to the other side. We are going to take the limit as x approaches x0 of f of x, and we are going to subtract f of x0 from it. Now, at first, what you're going to notice is that this right here is the only limit expression, but since this right here is a constant, we can drag it inside of the limit. So we actually take the limit of the difference of those two things, and this is going to be equal to 0. So if we can show that by differentiability, this equation right here does indeed hold, then we would be in for a win. We could show that the differentiability of f implies the continuity of f. And this is where we are going to start our journey. And this is why this proof is so cool and so nice and so short and so quick, because it's proof, because it's nice and short and quick and very sexy, and I just love it. We're going to start off with this one right here. We are going to take the limit as x approaches x naught of f of x minus f of x naught. So why exactly should you start with this expression? Because it's half the rent already. This is our halbe meter already of the differentiability. The only thing that's missing is divided by x minus x naught. And the cool thing with limits is that we can actually manipulate the inside of a limit algebraically. And in the limit, we can just multiply everything by 1 and nothing is going to change overall. So this right here is the limit of f of x minus f of x naught times x minus x naught divided by x minus x naught. Now, what we're going to do is we're going to just drag a bit of stuff around. We're going to take this x minus x naught in the numerator and drag it to the front. This part down here is going to go under here, leaving us overall with the limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught times x minus x naught. And now you might see this part right here is the differentiability condition of the function, and this right here is just some random arbitrary or factor. Now what we can do, if the limit does exist, we can actually pull the limit to each and every factor right here. Now the cool thing is the limit of just a polynomial, this right here is a linear function, always does exist. And this right here is the limit of the difference quotient. And it does exist by our original statement that f is actually differentiable. So we can take the limits individually. So this right here is the limit as x approaches x naught of f of x minus f of x naught divided by x minus x naught times the limit as x approaches x naught of x minus x naught. Now this right here is just f prime, as mentioned a second ago. And this part right here is going to go to 0, obviously, because if x approaches x naught, this right here is 0. 0 times this limit, which does exist, is going to be 0 overall. And lo and behold, we have shown that this equation right here is equal to 0 under the condition that f is differentiable. And this is exactly what we wanted to show, because this is the condition for continuity. And those were 5 short and quick proofs, which I really like, with a little aha moment when you do them and when you see them. I just love them. Tell me down there in the comments what you thought of those proofs, and tell me your most favorite short proofs down there in the comments below too. And if you want to see more mathematics that we did today, or maybe something completely different like physics or computer sciences, then the contents of today's sponsor Brilliant might be the perfect fit for you. Why should I tell you today about Brilliant when I do a video about proofs? I always tell you that Brilliant is mostly there for learning visually, interactively. It's not there to learn something hardcore abstract like you do in an abstract algebra class, for example, at university. They want to lay the groundwork for you. Now, this is exactly why I really appreciate Brilliant when it comes to proving stuff, because they do exactly what I told you a second ago. They take visualizations like this right here, which let you dive deeper into everything STEM. It really doesn't matter if it's proofs in mathematics or maybe something that you want to show in physics. There are plenty of proofs there too. Maybe it's also chemistry or computer sciences. It really doesn't matter. Brilliant gives you a better understanding of the things that you want to learn right now in a very visual, playful and interactive context. And the best way to experience Brilliant is by just checking out their amazing visualizations. As mentioned previously, it's not about learning something extremely hardcore abstract there. It's getting you started with the topics and maybe diving deeper into the topics as you go on with their courses. It gets abstract, don't get me wrong. It gets harder, gradually harder over time, the deeper you dive into everything that you are going to find in their courses. But they make it very, very user-friendly by including set visualizations, graphics, things that you can play around with using your own two hands to really learn something new on a daily basis, be it on the go, on your mobile phone, or at home on your PC. And you should just see for yourself if Brian could fill that hole in your educational heart in some kind of way by using my link here at the top of the description, brian.org/famblemeths, or the QR code somewhere up here in the corner. Try out the whole landscape of Brian for completely free. See if it's something for you. And if you feel like this could turn into a long-term relationship between you and their amazing services, then why not make sure to use my link in its entirety and get 20% off an annual subscription. It's seriously worth it. You should check it out. Brian is so fantastic. I just love what they deliver to the STEM community. A huge service to the STEM community is what they do for years on end. I just can't tell you how much I really appreciate what they do for all kinds of people around the world. And you should be part of the movement too. Brian is amazing. Check them out. It can't hurt. Try it for free and support the channel this way big time. And I hope you enjoy what you have seen today. And up until next video, I wish you guys a flammable day. See ya.